Dr. Ahmad Tamizi, and my metric number is 211092528. The title of my final year project is Design and Optimization of a Grid-Connected Solar PV System for Masjid Nurul Mutakin using PVC software. This project uses a simulation-based approach and the main tool is PVC software. The objective of this FYP, first, to design and simulate a grid-connected solar photovoltaic system for Nurul Mutakin mosque using PVC software. Second, to optimize the GCPV system of the mosque by improving energy production and reducing system losses using PVC software. Third, to analyze the system cost effectiveness encompassing payback duration and return on investment including evaluating environmental advantages. The main tool used in this project is PVSys. The reason why PVSys was selected because first, industry standard software for PV system design, which is widely used in industry and academia for PV system design and energy yield prediction. Second, includes technical and financial analysis, where it allows detailed customization of PV models, inverters, system losses, and also financial analysis. Third, accurate Malaysia weather database, which is included weather data from Metronome and enables accurate location-based performance forecasting. And the last one, support detailed component level modeling, where it supports economic calculations such as LCOE, payback period, and ROI, which are critical for project feasibility. This makes PVSys the most suitable tool for a complete technical and financial evaluation.
Now, I will demonstrate how I applied PVCs in this project. First, choose Grid Connected. And based on the recent project that I have done for this FYP, which is Masjid Nurul Mutakin, click it to load the project. And then choose New Site. The reason why New Site is being selected because we need to enter the coordinates to access the solar resource and put the longitude and latitude of Masjid Nurul Mutakin. After that, accept selected point and select OK. For the orientation, select orientation. I configure the system with a plane tilt of 5 degrees and azimuth 10 degrees facing true south, and no shading analysis was included due to the open rooftop. Choose the main parameters of system. Based on the manual calculations that I have done in FYP1, I used Jinko Solar for 475 watt, and for the inverter I used Huawei for 10 kilowatts. I used 18 PV modules of Jinko Solar, giving a total system size of 8.55 kilowatt per peak, which is equal to 8.6 kilowatt per peak per week. I then choose the optional of economic evaluations. I then input the installation cost using PVSys economic model. The total cost was RM38,475 ringgit, including PV modules, inverter, wiring, surge protection, pyrometer, installation, transport, and grid connection. A benchmark of RM4 ringgit 0.5 cent per watt per peak was used, and maintenance costs were estimated at 940 ringgit 0.5 cents, including inverter replacement and cleaning. After that, financial simulations were run to calculate payback period, LCOE, NPV, and ROI using a feed-in tariff that I use, which is 0.509, and a 10-year project horizon because it is according to SADA, which is at start year 2025. So this is the financial result based on installation cost, capex, financing expenses, and also ROI. And this is also the carbon balance where I use to do the analysis of environmental. After that, I run the simulations. Generate the PVSys report. This is the PVSys report. Based on the simulation, the PV system is expected to generate 30,347.27 kilowatt-hour per year with a performance ratio PR of 84.85% and a specific yield of 1561 kilowatt-hour per kilowatt peak per year. Next, let's take a look at LCOE. The LCOE is RM0.35 Malaysia ringgit per kilowatt hour, and the payback period is 5.8 years. This result aligns with benchmark from SEDA Malaysia and case study on similar mosque PV system, confirming the system is technically and financially feasible. And this is the CO2 emission balance. The system is also estimated to reduce 213.5 tons of CO2 over its lifetime. I also have done the optimization based on the angle, which is by comparing with the initial design, which is the original design, the plan set at 5 degrees. I do it and then I change it into 10 degrees, 15 degrees, and also at 20 degrees. Next, I also do an optimization based on sizing inverter by changing the nominal power of inverter, which is the original one is at 10 kilowatt. I change it into 50 kilowatt and then also at 17 kilowatt.
Despite its rare PVC has some limitation where assume fixed weather and pricing where it does not simulate real-time weather version or extreme conditions. Second, no-return schedule model where the output depends heavily on accurate input data like irradiance, temperature, and shading profiles. The accuracy depends on input data where shading analysis was skipped in this case, which might lead to overestimated energy yield. And the last one, result may differ slightly from the real-world performance. Why? The financial model assumes fixed rate for 10 years without considering policy or market changes. However, I minimize these issues by using conservative loss factors and relative cost inputs.
In conclusion, PVCs allowed me to design, simulate, and financially assess a solar PV system for Masjid Nurul Mutakib with high accuracy and detail. I gained valuable insight into technical modeling, system design, and the economic feasibility of PV system. This project improved my engineering skills in renewable energy design and enhanced my understanding of practical limitations in simulation tools. Thank you.